Again, a warm welcome to Walter and look forward to hearing from him. And this is something you're all very lucky to hear from him directly. Over the last 18 months, I have only been listening to him on the YouTube. So I must have listened to his lectures some 10 times. So it's really our privilege to actually listen to him first time. So over to Walter.
Thank you very much. Hello everybody, thank you very much for having us. Jehne and I, this is our first time in India and we really enjoyed, but actually we're really looking forward to a very good interactive discussion with all of you about what we've been doing, but how it applies in Andhra Pradesh and to our future. And really, I wanted to go through some of the background, what we're doing in terms of science and the ecology, regeneration of landscapes in Australia, globally, perhaps here in India, and really go through some of the technical background of why the processes, why things happen. And so I'll spend about sort of an hour or so talking about those different elements. But then really the biggest thing we would really value is your questions, and then we can have a lot of time both before lunch but even after lunch, and then to come back and to discuss and try to answer your questions. Right from the beginning, it's very important to say we don't have all the answers by any means, right? So it's not that it's all solved. Nature has solved it. She has got the solutions. And it's really up to us to look at nature, to see how nature has solved these problems, what can we learn from nature, and then how do we progressively take these natural safe solutions and make those applicable in our environments. The good news is, absolutely right from the outset, that there are solutions. We're going to have 10 billion people on this planet by 2050. That's the demography. And yes, we can feed 10 billion people. Yes, we can give you the water, the environments, the biodiversity, the cooling of the climate to have a habitable future for 10 billion plus into the future. Because it's not me saying that, there are natural systems that can deliver those outcomes. And the challenge that we have, and it is a very important challenge, what are we going to do to actually take those natural solutions, to learn, to ask questions, to refine better ways of doing things, and then use that natural lead to develop that regenerative agriculture, that regenerative biosystem that we all depend on. We all evolved on these biosystems, these ecosystems, and our whole everything, our sort of food, water, stability, everything depends on regenerating them. And we can do that, but it's just a question of we've got 10 years. 10 years before things collapse, get that serious. And then if that does collapse socially, then it's a very, very serious problem. So really it is now taking initiatives, taking innovations like zero budget natural farming, and really saying, right, these aren't just a new way of farming. No, this is a vehicle, this is a solution into the future. We have 10 years. How do we refine it? How do we multiply it? How do we extend it to secure that future? What Anne-Marie said, and Sophie said was absolutely right. Here is the UN, the FAO, the Sustainable Development Goals of the UN, and what we have to do to actually secure that. And the answer is zero budget natural farming, and these innovative regenerative agricultural systems can solve it. But we've got to start really focusing on making it happen. Now this morning we had very good discussions on some of the problems, like here is in a sense what's happened to Andhra Pradesh from the 1960s to where we are now, how we have actually lost that landscape. And basically, we also saw in the global context from Anne-Sophie how that is happening everywhere. The aridification, the degradation, the climate extremes as a symptom of that degradation. And so our challenge now is how do we turn that around? You know, where are the practical solutions? And of course, as we just already said, those solutions are in nature. And in a sense, nature started off in a very humble, simple way. If we go back when I was younger, about 4 billion years ago, you know, well, 4.6 billion years ago, we had a supernova, a cloud of hydrogen gas which formed a new sun, and stardust. The elements of the periodic table in stardust. These coalesced to form the 9 planets. The bureaucrats have dropped Pluto off the planet, but it's still there, don't worry, it's just the bureaucrats haven't recognized it. Okay, and so we've got the 9 planets. And the 3rd planet out from the sun, Earth, is in a sense our habitat. And then nature, over that last 4.6 billion years, has evolved exquisitely efficient systems to make it habitable. It started 3.8 billion years ago when, in a sense, the first living cell evolved. And we can go into some of that later on, but let's just fast track a little bit. But 3.5 billion years ago, some of those living bacterial cells learned how to photosynthesize. And what that involved is really a very nice, simple thing, because when you think of it, nature just had sunshine, CO2, water, nitrogen in the air, and stardust. That's all she had. That's all we've got. So how do we make that work to regenerate the planet, the hydrology, cool the planet, secure the future? And it's very simple, isn't it? Because nature simply took CO2 plus water, put in sunlight, and made carbohydrate. And of course produced oxygen as a waste product. To balance the equation, of course, we need 6 carbon dioxide and 6 water molecules. And that's really what photosynthesis is doing. It's really making biomass, it's making sugars, and really most 99.9% of life on Earth depends on this photosynthetic reaction from nature from 3.5 billion years ago, producing sugars, which then makes biomass and really builds everything. And this sugar is really stored, obviously as we can see it is stored sunlight, GHT, it's stored CO2, and it's stored water. We'll come into that stored water a little bit later, but that's all it is. It's just chemistry. And of course, when we use that carbohydrates, we will be generating energy, CO2, and water. Okay, and so really nature sort of used that as its building blocks for our biosystem. And when the oxygen in the earth had got high enough, more complex life was able to evolve, and the oceans then had more multicellular complex life, but they ran out of nutrients. And so that life in the oceans needed more nutrients because that became a limiting factor. And of course, those nutrients were from the rocks on the land. And so there was this competitive advantage if we can colonize those rocks. And so life forms grew from the marine edges onto the rocks to solubilize the rock. And as you can see, imagine there's the ocean, there's a rock, and so we had fungi. Fungi growing up onto the rock. Okay, they're not sexist. You can have fungals and you can have funguis. but we'll just call them fungi at the moment, right? Okay, so the fungi grew up onto the rocks because these are really microscopic tubes, and it's those tubes and the fungi have the enzymes to solubilize the rock and take that nutrient back to feed life here in the oceans. But the fungi are actually like us. They are actually proto-animals. Genetically, they're very, very similar to us. And of course, we can't photosynthesize. So the fungi very quickly had to say, look, I have to form a symbiosis. I have to form a marriage with these algae that could. And so they, in a sense, formed another life form, and Dee's already shown us those. These are the lichens. You see, and these are the lichens that then grow over rocks. And they're still with us, right from, actually this was only happening 420 million years ago. Before that, there was no life on land. But from 420 million years ago, these lichens then colonized rocks, solubilized rocks, and basically in that way created the nutrients to keep life going. But of course, by solubilizing that rock, it created for the first time soils. Okay, and soil is simply a mixture of mineral particles and organic matter, waste material, organic detritus. Because as these fungi and lichen grew, they kept on growing further and left behind organic waste material. And that actually then formed organic matter, which then in a sense formed the sponge. And because the sponge is so important, we'll put a red line around it because we remember it. Because what it's all about is restoring the earth's soil carbon sponge. Critically important. And so it's really powerful because this simple natural process of photosynthesis and then pedogenesis, the colonization of the rock by these lichens to create organic matter that created the sponge, is really the basis of terrestrial ecosystems. And we've just evolved as part of that process. So this is the foundation. So when we talk about we have to regenerate the Earth's soil carbon sponge, we're right down there, as nature did, rebuilding healthy ecosystems. It's very important to understand we have sun, CO2, water, nitrogen. We can't do very much about that as human beings, right? We don't influence the sky that much. The point of agency, the point of influence that we have at the planetary scale is all around the sponge. Okay? Because this is where humans influence the whole future life on Earth. There's two types of humans. There's one group of humans called Homo hubris, and they're very much in the degeneration business. Oxidizing the sponge to degrade biosystem. Homo hubris, right? But Homo sapiens, intelligent, conscious human beings, they're too smart. They realize this is nature. They're with nature, and they're in the regenerative business. They're investing in zero-budget natural farming. Okay? It's logic. Elementary. Okay. So it's a sponge is everything. So look, what is a sponge? And it's actually quite profound, or very simple. If we take a rock, here we have a rock, and there's, microscopically, there's a whole bunch of mineral particles, right? And that rock has a bulk density, it's heavy, it has a bulk density, just say from 2.6 to 3.5 grams per cc. And it's solid, it's heavy, but basically none of these nutrients and minerals are available because it's all locked up in a rock, isn't it? Now, if you did Dee's flour and water experiment and you put some water on this rock what would happen to the water? It would run off. It wouldn't infiltrate the rock. Okay, so basically, as we said, there's sun, CO2, water, nitrogen in the air, but it's really water and nutrients that are the limiting factor to life. That's what was going on here. And so really, to make life work from that rock, we have to sort of get access, we have to get availability to those nutrients, and we've got to hold water in that soil. And we do that through the sponge. Because as it's solubilized, these mineral particles, in a sense, separate. These little particles separate. And basically, they are separated and held apart, and you can draw it like little bed springs, if you like, by little bits of carbon. So the carbon, the organic matter, the detritus, is really keeping that soil matrix open. And again, Dee showed you Phil's photographs, and of course that was making the point that in this sponge, because we know its bulk density of healthy soil is 1.1 to 1.3 grams per cc, we know that 60% of healthy soils is made out of nothing. So if you want to build healthy soils, you add nothing. Or nothing. You add nothing. You just create structure. Because then you create these cathedrals in the soil, all these voids and spaces and these surface areas. And it's just by reconfiguring those voids and surfaces spatially in a less dense medium that nature creates water holding capacity, and nature creates biofertility. Because now you have this massive surface area of minerals all available for nutrient solubilization and uptake. You do it all by adding nothing. Just physical change. Okay, and so this is in a sense the healthy soil we talk about, and of course this is exactly what the sponge is. It's just simply creating solid rock, taking the solid rock, breaking it down with these microbial filaments and creating the residual organic matter, the bed springs, to keep that apart. And the amount of carbon we have to add, the amount of red bed springs, doesn't have to be big. If we have 3% by weight of organic matter, that's more than enough to create the sponge. So next time you go into a cathedral, just think of it. You don't look at the rocks the cathedral's made out of. You know, here are the bricks, they're beautiful granite bricks. Vijay doesn't even look at the cement between the rocks that holds them together. But he looks at the cathedral, the spaces, the voids, the social capital, the habitat that is created. And so it is with a sponge. And really, it's this sponge and creating that in our soil, that is our point of agency. That is where we humans can go from being Homo hybris to going to be Homo sapiens and regenerating the future. Okay? And so that's the very powerful message that we have to do. And it has a profound effect, because by creating this sponge, we can now infiltrate and retain moisture. Dee showed us a beautiful photograph. No, they weren't beautiful, they were horrible photographs. From Vermont to basically the flooding and the erosion and the damage because the water couldn't infiltrate. And it's actually quite profound. Now, these figures will vary a little bit, different parts of the world where you are, because different landscapes, different soils, different climates, but really only vary by several percent. But let's take the data from Australia, where we've done this study in quite detail. We'll go here, and see that we look at that. If we have 100 raindrops, You see, and let's hope we still have 100 raindrops. We're not going to have that, but let's at the moment still be living in hope that we have 100 raindrops. The issue isn't that we get 100 raindrops. The critical issue is what happens to those 100 raindrops every time they fall. And we had this sort of people from the people in the field showing us the diagrams to say, yes, we got 40 millimeters of rain in July, we got another 60 millimeters in September, and the real issue isn't that we got 60 millimeters in September, but what happened to every one of those raindrops for the 60 millimeters. And of course we know, logically, that 99 out of 100 raindrops obviously fall on soil, because it comes from the air and falls on the landscape. I mean, this is the rain falling on the land. I mean, obviously it also falls over the ocean, but the figures are different there. 99 drops fall on the soil, but rarely do more than 12 drops end up in streams and rivers. Okay, I mean, if you've got a concreted catchment, you'll get more, but very rarely in nature more than 12. And very rarely can we hold more than 2 in our dams. Okay, so all our investment in dams globally, and since the Second World War, the World Bank has invested, Asia Development Bank has invested in building over 50,000 large dams. UN knows all about it. 50,000 large, 3,000 to 10,000 gigaliter, billion litre dams. And they're all drying, they're all silting, and they're all just sort of basically saying, look, we have water, but it's only useful where and when those dams are, because water is extremely expensive to move around as liquid water. It's so heavy. Okay, but out of 100 raindrops, we've got 2 in our dams. And at the moment, those 2 drops out of dams really drive all our hydrology, our industrial hydrology globally. Of those, 70% is used in farming, 20% is used in industry, and you'll be surprised to know, perhaps not, but a lot of that is to generate power, for electrical cooling stations and what have you. And perhaps 10% is used domestic. Okay? And so we are now put a society which is in an acute water crisis. Mark Twain said it in 1890. Whiskey is for drinking, water is for fighting over. And we now, 100 years later, 120 years later, say that was a very wise man. Right, but wise. Okay? Because it is water that is going to be the critical